Welcome back to Chem 4300. In this video, we're going to continue Chapter 14 on radiating dipoles in quantum mechanics. And in the last video, we saw how Rutherford's model of the atom was actually okay as long as he said that his electron, which was orbiting around the nucleus, was in an energy eigenstate of the Hamiltonian. Because what we learned was that when an electron's in an energy eigenstate of the Hamiltonian, that wave function has an expectation value for the electric dipole moment that is time independent. It doesn't vary with time, and so because of that, it doesn't radiate away any energy, and so that electron orbit is stable. We also saw that it's possible for an atom or a molecule to radiate away energy or absorb energy when it's in a superposition of energy eigenstates. And in that superposition of energy eigenstates, we saw how that can take place and what are the terms that were important, which were things like the transition dipole moment and the energy difference, and the coefficients in that superposition, which told us about the time scale at which that transition took place. But we still then have an issue of how that atom or molecule, which was in an energy eigenstate, managed to get into that superposition of energy eigenstates and start this transition where it irradiates or absorbs light. So that's the issue that we need to address next. And of course, one way that you can do that is to kind of push that state, that energy eigenstate, into a superposition with one of those other energy eigenstates. And you can do that by shining light on the atom or the molecule. So we're going to be talking about different types of interactions between an atom or a molecule and light. And one is just talking about the absorption of that atom or molecule as it goes from one energy eigenstate to a higher energy eigenstate. Another case will be what's called stimulated emission. So I said you have to push somehow that atom or molecule in order to get it to emit light by putting it in that superposition state. And we do that by shining light on the sample to put it into a linear combination of two energy eigenstates. Excuse me. Another possibility that we have to also admit that we have to work with here is that there are cases where there is absolutely no light shining on an atom or a molecule, and it's in its excited energy eigenstate and with no light present, so no apparent way that it's being pushed into the superposition states, it will still manage to undergo a transition and emit light going from one energy eigenstate to the other. And this one is a little more challenging to explain, but we'll come back to this later. What we're first going to talk about is how the interaction of an atom with light can lead to absorption and stimulated emission. So when we turn on light, we shine light on an atom or a molecule, we are subjecting it to some oscillating electric field. We're also subjecting it to an oscillating magnetic field, but the electric field interaction with the electric dipole moment is what we're primarily interested in here. So let's take a simple case of a sinusoidal type oscillation. So we have light, which is just with a single frequency, say omega, and it's oscillating. And with this addition of this interaction between the electric dipole moment and the electric field, our total Hamiltonian becomes the Hamiltonian when the electric field, the oscillating electric field is off, and then this extra term here when it's on. So our Hamiltonian will be changing depending on whether the electric field is off to when the electric field is on. Now, one thing you may have noticed is there's no R dependence here, and what I'm going to assume is that the light wavelength is very, very long compared to the size of the atom or molecule that we're looking at in the transition. So if that's the case, then we're just seeing a uniform electric field that's just changing uniformly with time, and we can ignore the time dependence. It's only when you get to really short wavelengths that you have to start worrying about that effect. But for what we're looking at now, we can ignore the spatial part in this oscillation. So, as I said, when there's no time-dependent perturbation present, then the stationary states of the Hamiltonian are associated with this term here. But once we turn on the light, when we add this term, this becomes the new Hamiltonian, and the old energy eigenstates, in a sense, the old ones, the ones that are associated with this Hamiltonian, are no longer the energy eigenstates. So now there are new energy eigenstates, and an old energy eigenstate becomes a linear combination of the new energy eigenstates, and that's how we push to cause this transition to occur. So let's see how that happens. So we can imagine then that the state of our system, our wave function, is some linear combination of these energy eigenstates associated with the Hamiltonian when there is no perturbation present, so that when there's no light shining on our atom or molecule. And so what we're going to take is some initial condition where we start out in one particular energy eigenstate. Here we're going to say n, and we're going to have all the other energy eigenstates in this linear combination be 0 at time 0. And what we're going to do then is we're going to use the full Hamiltonian when the perturbation is present, and we're going to solve the time-dependent Schrodinger equation. So we're going to take this equation with this Hamiltonian, and we're going to solve it. Well, we're going to do sort of a Taylor series expansion and a lot of work, and later, after many steps, you'll find this result. So leave this as a homework assignment, say, for you to work this out. But you find that the rate of change of these AMs, the ones that are initially not populated, the rate of change of those guys is given by this integral here, minus I over h bar, and the integral of the perturbation, the sandwich of the perturbation with the energy eigenstates, and we see we have the cross terms here between the different energy eigenstates. So for the mth energy eigenstate, its rate of change is going to require us to use the nth, the original, the one where it's originally populated energy eigenstate, the m state, the one that we're trying to evaluate, and then we're going to evaluate this integral, and that's going to give us the rate of change for the growth of that state. So if I take my perturbation in the actual form I have here, I take my energy eigenstates, I plug them into that expression here, then I get this term right here. And you can just check that. It's not so bad. And what you see is that that transition moment integral that we talked about earlier shows up right here. Here we see the oscillation with the frequency, which is the difference in the energy eigenstates. And then here we see the driving potential, the electric field with that oscillation there. And that's going to give us this rate of the mth state's increase in its contribution to the superposition of states. So here we have our initial conditions here, and if we take this result, we can turn that into this solution here. Again, this is after many steps. I'm skipping some things. This is something you can try to work out in your homework if you like, but I'm just going to give you the result here. This is the time dependence of the amplitude, so the squared, so the AM squared is going to be related to this transition moment here squared times time divided by these constants, and this is the radiation density that is present in this, of the light that's hitting the sample. So even though we use this sort of single frequency here, we assume that there may be many frequencies of light that's shining on our sample. What is most important is the frequency that the light that has this frequency of omega mn, or in this case nu mn, which is the radiation density. So this is the radiation density, the amount of light at that particular frequency. So that's something you could get, for example, if you had a black body light source, and you could just use the Planck's black body expression to get the value for that U there for at that particular frequency. So then the rate at which our transition from this n state to a given m state is going to be given by, just taking the derivative of this with respect to time, is going to be given by that expression there. So now we've worked out the rate at which light can be absorbed, or the rate at which the light will stimulate emission between energy eigenstates of n and m. All right? Now, that's great for the stimulated emission, but we still have this issue of spontaneous emission. where there is no perturbation present, and still a system that's in an excited energy eigenstate can manage to go into a superposition state and radiate away the light. Now, so far we've been treating this all with classical E&M. We haven't been talking about photons. We've been treating light classically. We haven't been thinking about light in terms of a quantum treatment of light. And to do that, we would need quantum field theory, and for light, that's called quantum electrodynamics. And it's really in that realm of quantum electrodynamics that you can see the reasons why the spontaneous emission can occur. So I don't really want to get into that. That's beyond the scope of this course. What we're going to do is look at Einstein's approach for taking the stimulated emission and absorption of an atom or molecule interacting with light and using that to learn about the rate of spontaneous emission that might be present. So he did this without actually even knowing Schrodinger's wave equation or quantum electrodynamics. He was able to work out the spontaneous emission rate based on the rates that we just calculated, which is pretty impressive. So, but if you wanted to go into detail about what actually causes that push of the energy eigenstate into that superposition, what causes spontaneous emission, you really need to go into the area of quantum electrodynamics. So what we're going to talk about is this paper that came out back in 1916 by Albert Einstein, where he was looking at the absorption and emission of light. So let's just take a look. First of all, we know that Einstein had available to him in 1960 Planck's distribution law for that energy density of light at different frequencies. And so he was going to use that. And he knew that for light absorption to occur, that there was some light absorption rate from, say, level N to level M that depended on the light frequency. So he sort of reasoned that, you know, light is in some kind of resonant phenomena. So with the light frequency on resonant with the atom's transitions, that there should be some rate of absorption. And that rate he has here is equal to this expression here, where these terms are N is the number of atoms that are actually in the nth state that are about to be excited. U is that energy density with the evaluated at the frequency that is associated with the transition from N to M. And B is this proportionality constant that's yet to be determined, which relates that rate to the number of atoms, the energy density, and this proportionality constant. So that's for light absorption. For light emission, he proposed two processes. He said we can have spontaneous emission where there's no light present, and we can have stimulated emission where we have some light that's going to be present. So these are the same pictures that I just showed you earlier. So for the spontaneous emission, there's no light present. He said that the rate of spontaneous emission is just going to be the number of atoms that are in this excited state, Nm, times some yet to be determined constant, some coefficient, which is the spontaneous emission coefficient, which is going to give him this spontaneous emission rate. So this is his proportionality constant, and he knew, of course, that that all dipoles will oscillate, all oscillating dipoles will radiate, and he figured the same was going to be true for atoms. But remember, he didn't know about the Schrodinger equation and stationary states. He didn't know that an atom in a stationary state wouldn't radiate, because this was 1916, right? So he was okay in thinking that this was what's going to happen. For the stimulated emission, he guessed that the rate was going to be similarly proportional to the number of atoms that are in the ground state or the lower state, the energy density that matches the frequency between N and M, and then again a proportionality constant, which we're going to call Bmn, which is the proportionality constant for the stimulated emission. So just to go back here real quick, I mentioned this is the proportionality for the absorption, which is Bnm, and then for emission, he has a proportionality constant that's Bmn. So we switch the integers here, marking the states. So what we're going to do is now see what kind of relationship we can find between these coefficients. So taking them all together, what he said was that the absorption and emission rates are going to be equal at equilibrium. And so this is the absorption rate going from N to M. In the emission, there's two contributions. There's the spontaneous contribution and there's the stimulated contribution. So here's absorption, here's emission, and those two rates have to be equal at equilibrium, at thermal equilibrium. So taking his expressions that we saw on the earlier slide, here is the absorption rate, here is the emission rates here. These have the common NM, so it gets factored out. And then using Boltzmann's distribution law, if you remember Boltzmann's distribution law here, which is going to be related to the energies, e to the minus em minus en over kBt, that's just e to the minus h bar omega over kBt, then you can rearrange this expression up here with these n's here given by Boltzmann's distribution, and you can rearrange this term over here on the left to be this term right here. Okay, so you can stare at that for a second here. You can see that using the Boltzmann energy distribution, he can rearrange this expression here into this form, like this. Rearranging this further, then you can write down that the energy density is going to be equal to the spontaneous emission coefficient divided by the stimulated and absorption coefficients with this factor here now present. So this expression he derived completely then from this very simple model, and he got an expression for the energy density that looks very similar to what Planck found. So if you take Einstein's derivation and you equate it to Planck's result, then you can see that the only way to make this true is that to get this e to the h nu over kBt minus 1 present in the denominator over here requires that these two b's actually have to be equal to each other. So the stimulated emission and absorption rates have to be equal in order to get agreement of Einstein's expression with Planck's expression. So if you do that, then you can just have one value, which we'll write like this, and then we can identify this term from Planck with this ratio here in Einstein's expression. And so what we end up with finally is that we get A over B is given by this expression here. I forgot, maybe I didn't mention it. There is a term over here that's a little bit different, and there's some differences there. But when you make this, equate all these guys, you get this expression here for the ratio of AMN over BNM, and that's given by this. So this is the relationship between the spontaneous and the stimulated emission rates. And Einstein worked all this out without even knowing about quantum theory of Schrodinger, like the wave equation or electrodynamics, quantum electrodynamics or anything like that. He worked out the rate of spontaneous emission to stimulated emission is given by this expression here, where it's proportional to the frequency to the third power with the rest of these constants here. So if you go back then to Schrodinger's picture, where we actually derived earlier this rate for the light absorption, then we can use that and equate that here. We can derive this BMN coefficient in terms of the expression that we had earlier, and then furthermore go back and get that spontaneous emission rate here from that expression. So we can calculate then the spontaneous emission rate using Einstein's approach and this expression that we derived for stimulated emission and absorption, that to give us this spontaneous rate. So even though we didn't have the sort of the theory, the quantum electrodynamics, to work out the spontaneous rate from first principles, we were able to get it out of this clever approach that Einstein had put together. And you see that the spontaneous rate is proportional to the frequency to the third power, the transition moment, dipole moment, which is squared here, and then the rest of these are constants here. And so actually for the first excited ground state of a hydrogen atom, you can take the energy, the frequency associated from that to the ground state, and you get a rate of about 10 to the 8th transitions per second, which is for the spontaneous emission, which is pretty much in agreement with what you get there. So the reason why we didn't do quantum electrodynamics is a little bit more complicated, but if you did that kind of approach, what you find is that light is described in terms of kind of a harmonic oscillator picture, and there is a 0-point energy that allows that even in the vacuum, some kind of 0-point energy fluctuations that will be responsible for generating this type of spontaneous emission rate. So we'll leave it like that. These are what we call vacuum fluctuations, and they can stimulate this type of emission, the spontaneous emission. But it doesn't really matter for us because we now have an expression in terms of the stimulated absorption and emission. Okay, so that's it for this video. In the next video, we're going to be looking at selection rules for transitions.